So in this video, we're going to look at problem 2.86. We have an assembly here. A part of the assembly is a rod that extends from two reference points, which they've denoted, A and B. And what we're asked to do is to formulate a Cartesian position vector from A to B. That's just a fancy way to say, write an expression for a position vector from A to B in terms of its x and y coordinates, and then components, I should have said, and then determine the rod length from A to B. So basically what's going to happen is if we draw a position vector that goes from A to B, we're going to talk about the process for doing that. But remember, for all position vectors, if you just know the coordinates of all vectors have a tail and they have a tip. If you know the coordinate of the tail and you know the coordinate of the tip, you just subtract the coordinates of the tip from the tail on a per kind of component basis, and that allows you to get the position vector. If that position vector goes along that rod, then the length of that position vector also corresponds to the rod length. So that's all that we need to do. We need to read out the coordinates of A and B, follow our rules for writing a position vector, and then take the magnitude of that position vector. So let's actually look at the solution of this. And when I redrew the problem, I didn't draw any of the actual assembly on there. I just drew the 2 points of interest because that's all that we really need to know. This point A, which is down here in the fourth quadrant. Remember, we're not necessarily working with vectors here, but it's going to feel a lot of the same way, because if I want to determine the x coordinate of this point, I can again do sort of a right triangle decomposition as I'm showing you here. And what we see is that the x coordinate of that point is going to be related to the cosine of this 30-degree angle since it's adjacent. So I'll take the hypotenuse, which in this case is 150 millimeters long. I'll multiply by the cosine of 30 degrees, and then I'll adjust it since it's going to the left. And what that's going to tell me is that the x-coordinate of point A is minus 129.9038. In a similar fashion, I can find the y-component by multiplying that length of the hypotenuse times the sine of 30 degrees. Again, since it's in the downward direction, it also needs to be adjusted to be negative. Fortunately, B lies directly on the y-axis, so I can just read out its coordinate directly. It is at point x equals 0, y equals 300. If I want to draw a position vector from A to B, meaning that the tail is at A and the tip is at B, the rule for doing that is I take the coordinates of B and I subtract away the coordinates from A. And that's all that this is showing here. That position vector will have an x component corresponding to the B x coordinate minus the A x coordinate. In a similar fashion, the y component, or the j hat component, will be the y coordinate of B, because that's where the vector actually ends, that's its tip, minus the y coordinate of A, which is its actual tail. So just be careful with your math here. When you subtract a negative, that will become positive. Same thing over here. And always easy, it's good to just do a sanity check here and ask yourself, this says that the position vector from A to B has a positive x component and a positive y component. So what you ask yourself is, if I were to go from A to B, do I need to move in positive x and positive y? Yeah, I do. So that gives me kind of a sanity check that this could be a reasonable answer for the position vector. Obviously, I don't know what's correct yet, but assuming I can do arithmetic, we'll be okay. So if this is the position vector that goes from A to B, if there were a rod that were aligned on that position vector, I could determine the length of the rod by simply finding the magnitude of that position vector. And for all vectors, if I want to find their magnitude, I use Pythagorean's theorem. I take the square root of the sum of the individual components squared. And if you do that, round it to 3 sig figs, you will get 397 millimeters. So this is the position vector in Cartesian form. And this is the length of that rod, since the rod actually lies along the position vector.